Hey guys, today actually I got a really interesting integral for you to solve, and it's the integral from 0 to infinity of sine squared of x over x squared. So there are lots of ways that you can solve this integral, but the approach that I like is Feynman's trick of integration, and that includes introducing a parameter I of t that includes the function to be from 0 to infinity of sine squared of xt over x squared dx. And if I find the I of 1, I'm going to be able to get sine squared of x over x squared dx. And what I'm gonna do is I'm gonna change the form of this integral, and that's it. So um, for that, you must know that if I have, for example, an integral here, so let me write it in this color. It's a great remark. This, if I have an integral a to b of f of x and t with respect to x, and I take the derivative with respect to t, um, I can take the derivative of this integral with respect to t, the multivariable integral, and my d dt of I, according to Leibniz rule of integration, is going to be the partial derivative with respect to t of f of x t dx. So this is going to be partial. It's partial derivative. Now, let's recall the integral that we had here from 0 to infinity of sine squared of xt over x squared dx. Now, what I'm going to do, I'm going to take the derivative of both sides with respect to t. So it's going to be sine squared of xt over x squared dx. And this here is going to be I prime of t, and this is going to be going inside. It's going to be going inside, and my I prime of t is going to become a multivariable, a partial derivative here. So what I'm going to have is a partial t, the integral of sine squared of xt over x squared dx. Now I can take the derivative of this function partially, and actually I don't need to use the chain rule, or I don't need to use the equation rule, because the x here is constant and the only variable here is t, and the only thing that we can find t in is sine squared x, so thus we have to derive sine squared x. Thus I prime of t is the integral from 0 to infinity. I'll take the derivative here. It's going to be 2 sine xt cosine xt over x squared dx multiplied by x. So multiplied by x, so we can have we can cancel these two out, and my I prime of t therefore is going to be integral from 0 to infinity. 2 is going to be here of sine xt cosine xt over x dx. My I prime of t therefore is the integral from 0 to infinity of this identity, goes down to 2 sine sine of 2xt sine of 2xt over x dx. Yeah, that's right. And so this 2 shouldn't have been here. This should have been included here. So now what I'm going to do, I'm going to do a changing variable. I'm going to do substitution. I'm going to say u is 2xt. And if I differentiate, what does that mean? Differentiation, it means that I gotta differentiate both sides and say with respect to what variable I've differentiated. So for this one, it's going to be the differentiation. It's going to be du equals 2dxt, and my dx is actually du over 2t. Thus dx I can write it as du. Never mind. And actually, I wanted to do that. X is going to be u over. It's going to be u over 2t, and I can write x as u times 2t to the power of -1, and you'll see why I did it. And I prime of t of mine is going to become the integral from 0 to infinity of sine of u over, so the x is u2t to the -1 du to the 2t. These two powers annihilate, and I'm going to be getting I prime of t to be equal to the integral from 0 to infinity of sine u over u du. Now I can use a trick here, and I can so actually this integral is still unsolvable in terms of elementary functions. We're going to use the Feynman technique again. I'm going to call I2 to be equal to the integral from 0 to infinity of sine u over u du. Actually, to make it work much simpler, I'm going to say I2 equals to the integral from 0 to infinity of sine x over x dx. So I gotta find the value of this integral so it can be connected to this one. Here again, we're gonna do a parameter introduction, 0 to infinity. I'm gonna say e to the negative tx sine x over x dx. Why? Because you'll see that this integral, when we integrate it, will converge eventually. So if I find I2 of 0, I'm going to get the integral of sine x over x dx. So my goal should be to find I2 of 0. Now again, I can take the derivative with the rule that I mentioned. I prime 2 of t is the integral from 0 to infinity of partial t of e to the negative tx sine x over x dx. And the I prime 2 of t is the integral from 0 to infinity of negative x e to the negative tx sine x over x dx. And notice that how perfectly these two x's are going to cancel out, and I'm going to be left with the I prime 2 of t. Better. I prime 2 of t is the integral from 0 to infinity negative e to the negative tx sine x dx. Now what I can do here, this integral is actually solvable. I can use the integration by parts, which is defined as the following. If I have a u dv, this u dv is defined as uv minus v du. So I'm going to define my u to be this one and dv to be this one. So my u is negative e to the negative tx. My du differentiation is t e to the negative tx dx. And my dv is sine x dx, and antiderivative of it is negative cosine x. Because if you take the derivative of negative cosine x, you're going to get sine x. So I prime of t is negative e to the negative e to the negative tx minus cosine x, the integral from 0 to infinity, the limit, so the u and v. So the next part is minus the integral from 0 to infinity of negative cosine x times du, du, t e to the negative tx dx. So these two negatives are going to cancel out, and I can write my I prime of t. So first of all, let's evaluate this limit here. E to the, let me write it in red, negative e to the negative tx. So this is going to be, these negatives are going to cancel out. I'm going to be left with negative tx cosine x from 0 to infinity. And I'm going to take the limit as x approaches infinity of e to the negative tx cosine x minus the limit as that's not a limit, actually we can say e to the 0 cosine 0, and cosine of 0 is 1, e to the 0 is 1, so it's going to be 1, and these limits cosine of infinity is always going to oscillate between 0 and to infinity, but e to the negative infinity is 0, so this term is going to be 0, and I'm going to be left with negative 1. So this limit, the evaluation of this limit here is negative 1. So I can write, I prime of t is negative 1 plus the integral from 0 to infinity t e to the negative tx cosine x dx, and the I prime of t is negative 1 plus t, the integral from 0 to infinity of e to the negative tx cosine x dx. Now for this one, I gotta do the integration by parts again. So this is gonna be u and dv. U is gonna be e to the negative tx. Du therefore is negative t e to the negative tx dx. Therefore my dv is gonna be cosine x dx, and v is going to be sine x. So I'm going to do this integration by parts again. I prime of t is constant negative 1 plus t times u. U is e to the negative x, e to the negative tx times sine x from 0 to infinity minus the integral from 0 to infinity of v du sine x, which is sine x negative t e to the negative tx dx, and it's going to be it. So I prime of t is negative 1 plus t. This limit is going to go down to 0 if you calculate it the way that I did here. So it's going to be 0 plus, minus t, the integral from 0 to infinity of minus e to the negative tx sine x dx. Why did I keep the minus here? Because this is exactly our I prime of t. Actually, I prime second of t that we were trying to find, and I prime of t is going to be negative 1 plus t times negative I second prime of t, should have been second prime of t as well. And I'm going to get forgot to put t here, so it's going to be t squared. It's going to be t squared I prime 2 of t. And if I move it to this side, I'm going to get I second prime of t is negative 1 over 1 plus t squared, which if I integrate, I prime second of t is negative 1 over 1 plus t squared dt. This is actually the integral, the derivative of arctan of x. Thus, we're going to have negative arctan of t plus c. Now my I2 of t is going to be this. Remember the I2 of t, the integral from 0 to infinity of negative e to the tx sine x over x dx is negative arctan of t plus c. So now I'm going to take the limit for finding this constant of integration, because it's very important. Limit as t approaches infinity. Why? Because this decays, e to the negative infinity decays. So e to the negative tx sine x over x dx equals to limit as t approaches infinity of negative arctan of t plus c. So this decays, which means that this integral is going to go down to 0, because the definite integral of 0 is 0. And I'm going to be left with the limit as t approaches to infinity of negative arctan of t plus c. So arctan, if you see the graph, it will look like something like this. And the arctan, so this is the asymptote of pi over 2. So as it goes to infinity, for example, here is infinity. Infinity is a concept. It's a very large number. For example, 1 billion, a very large number like this. The arctan of it is going to be approach pi over 2, the asymptote of pi over 2 here. Thus, I can say the limit as t approaches infinity of negative arctan of t is a negative pi over 2. Thus, c minus pi over 2 equals 0, which means c equals 0. And if I write this again, I second of t sine x over x e to the negative tx dx is negative arctan t plus c. And if I let t be equal 0, it's going to go down to 0 and 1, and it's going to be sine x over x. And we saw that the constant is pi over 2. Thus, this integral, the arctan of 0 is 0, and the integral from 0 to infinity of sine x over x dx is pi over 2, which means the value that we were left with here, the work here, where were we? Okay, the I prime of t that we got, I prime of t from 0 to infinity of sine u over u du, these values pi over 2 exactly. Thus I prime of t is pi over 2. And I'm going to integrate it again. Thus I of t is pi over 2t plus c. And again, I want to find the constant of integration. I'm going to write the I of t, which is the integral from 0 to infinity of sine squared of xt over x dx, which is pi over 2t plus c. And if I let t be equal to 0, t approaches 0, I'm going to find this is going to go to 0, this is going to go to 0, the c equals 0. Thus, the integral from 0 to infinity of sine squared of xt over x squared dx is pi over 2t plus 0. So I'm not going to write it. What happens if I let t be equal to 1? Well, I'm going to get the integral from 0 to infinity of sine squared of x over x squared dx to be equal to pi over 2 times 1, which is pi over 2. is really interesting result. So the integral from 0 to infinity of sine squared x over x squared dx is pi over 2. And that concludes this video. Please let me know if you have any questions. I will respond to all the comments, and I'll see you next video.